All right, today we're going to unlock a totally hidden world. I'm talking about the trillions of molecules that make up, well, everything around us. And each one has its own secret identity. So we're going to learn how to see them, but not with our eyes. We're going to use a special kind of light. So that's really our big question, isn't it? How can you possibly identify something you literally can't see? I mean, how does a scientist in a lab tell the difference between two white powders that look exactly the same when one might save a life and the other could be incredibly dangerous?
Well, the key is kind of hidden in plain sight, or actually just beyond plain sight. What you're looking at here is the electromagnetic spectrum. It's this huge range of light, everything from radio waves all the way up to gamma rays. In our eyes, we can only see that tiny, colorful little sliver right in the middle, but the tool we need, it's lurking right next door.
All right, so let's dive into this invisible rainbow. You see, to find the right tool for the job, we first have to get this one key idea. Different kinds of light interact with matter in completely different ways.
Okay, now this is really interesting. Take a look at how this all breaks down. You've got super high energy stuff like X-rays that can just blast right through to the core of an atom. Then you have microwaves, which, make molecules rotate. But look right there in the middle, infrared light. It has that perfect kind of Goldilocks amount of energy for one super specific, super useful job, making molecules vibrate.
And honestly, that is the key idea for this whole thing. When infrared light hits a molecule, it doesn't just sail on by. Nope, it gets absorbed. And all that energy makes the molecule shake and move in its own unique way. You could say it makes it dance.
So it follows, right? If we can just figure out the specific dance moves of a molecule, well, then we can figure out its identity. So let's get ourselves a front row seat to the molecular dance floor.
So the thing is, molecules are never perfectly still. Their atoms are always jiggling around, constantly moving. We call this molecular vibration. Now, what infrared light does is it's like a song with the perfect beat. It hits that molecule and makes its natural jiggling, its natural vibration, way more intense. So intense that we can actually detect it.
So let's break down the two main dance moves here. First up, you've got stretching. This is where the atoms in a bond move further apart and then closer together. Just like a spring being pulled and released. And then you have bending, which is where the angle between the bonds changes, kind of like a pair of scissors opening and closing. And here is the absolute crucial point. Just like it takes way more effort for you to do a big jump than a simple shuffle, it takes more energy to stretch a bond than it does to bend it. And what's more, different types of bonds, like, say, a carbon-oxygen bond compared to a carbon-hydrogen bond, they all stretch and bend at their own unique energy frequencies. This is what gives every single molecule its own signature rhythm. Okay, so we know every molecule has its own unique dance moves. But how in the world do we actually see this? How do we record the performance? Well, for that, you need a special kind of camera. It's called a spectrometer.
And wow, has the technology come a long way. Today's instruments, they're called Fourier Transform Infrared Spectrometers, or just FTIR for short. They are just incredibly fast and ridiculously sensitive. I mean, they can capture the entire dance routine of a molecule almost instantly.
The secret to all that power? It's a really brilliant piece of engineering right at the heart of the machine. It's called a Michelson interferometer. And the way it works is, well, it uses a very clever trick with light to get us exactly the information we need. Okay, so check this out. Here's how it works. A beam of infrared light, one that has all the different frequencies, it enters this interferometer. First, it hits a special beam splitter. This thing sends half the light down one path to a mirror that's just sitting still, and it sends the other half down a second path to a mirror that's constantly moving back and forth.
Right. So then the two beams bounce off their mirrors and they're brought back together. But because one of those mirrors moved, its light beam has traveled a slightly different distance. So when they recombine, their waves interfere with each other, and this creates a really complex signal. And that signal, once it's passed through our sample, now contains all the information about which specific frequencies of light the molecule soaked up to do its dance. It really is a little bit of physics magic.
Okay, we've captured the dance. Now it's time for the big reveal. How do we take that super complex signal and translate it into something that a person can actually read and make sense of? So a computer does a really fast mathematical operation on it called a Fourier transform. And what we get is this, an IR spectrum. And this graph,
This is everything. This is the unique, the undeniable, the fingerprint of that molecule. I'm serious, no two different molecules will ever have the exact same one.
And reading it is actually way more straightforward than it looks. The bottom axis there, the horizontal one, that's the frequency of light. You can think of it like the different notes on a piano. The vertical axis, that just shows how much of that light made it through the sample. So when you see a big, deep value like that one, that's the gold. That's a frequency the molecule totally absorbed, using that energy to stretch or bend one of its bonds.
So yeah, every single one of these dips, or peaks as chemists actually call them, is a direct record of a specific molecular dance move. A peak way over at a high frequency, that could be a really strong bond stretching. One at a lower frequency, maybe a bending motion. It's literally a complete map of how that molecule dances.
And that brings us to the most powerful part of the whole graph. You see this really complex area over on the right with all those unique little peaks and valleys? That's known as the fingerprint region. I mean, sure, other parts of the spectrum can tell you about general types of bonds, but this region is absolutely 100% unique to that one specific molecule. It is the ultimate proof of identity.
So that's the science, and it's really cool. It's super clever, but why does it matter? What's the point? Well, the ability to identify any molecule has absolutely enormous consequences out here in the real world. Yeah, this technology isn't just stuck in some lab somewhere. It's like a silent guardian in our everyday lives. Just think about it for a second. Forensic scientists use it to match a single tiny fiber from a crime scene. Pharmaceutical companies use it to guarantee that the medicine you take is actually pure and not some dangerous counterfeit. I mean, from the plastics in your phone to the food you eat, this technique is working behind the scenes all the time, checking the molecular makeup of our world to help keep us safe. So the next time you look at, well, pretty much anything, just remember it has a hidden identity. It has a unique dance, written in a language of light that we've only just learned how to read. And that really leaves you with a pretty big question, doesn't it? If we have the key to unlock these molecular fingerprints, what other invisible secrets are just waiting to be discovered all around us?